All right, let's get right into it. We are about to tackle one of the most important, but maybe one of the most misunderstood concepts in all of physics. Seriously, this is a single idea that pretty much governs everything, from the very beginning of the universe and how stars are born, all the way down to the reason you and I are even here to think about it.
And to show you just how misunderstood this idea is, we only have to ask one really simple question. What does planet Earth really get from the sun? Now, the obvious answers are, heat, light, energy, and you're not wrong. But that is not the whole story, not by a long shot. So here's a fact that might just blow your mind. Let's look at the basic energy balance of our planet. For the Earth to keep a stable temperature over, billions of years, it has to radiate the exact same amount of energy back out into space that it gets from the sun. It's a perfect balance. 100% comes in, 100% goes out. Which of course leads to a fantastic puzzle. If every bit of energy that comes in just goes right back out, what are we actually gaining from it all? If it's a zero-sum game, what is the sun's real gift that makes all of life possible? Well, to find that answer, we need to jump back in time a couple of centuries, right into the middle of the Age of Steam.
Okay, this is where we start to really unravel this mystery. And believe it or not, it all kicks off with the Industrial Revolution.
Let me introduce you to Sadi Carnot. Back in the 1820s, he wasn't thinking about planets or stars. He was thinking about something much more down-to-earth, steam engines. He saw that these incredible machines, the super high-tech of his day, were actually shockingly inefficient. They were only turning about 3% of their heat into useful work. He just had to know why, and in trying to solve that problem, he accidentally discovered a fundamental law of the entire universe.
Carnot's big idea led to a concept that some people call the law of spreading out. And it's a rule that applies to, well, everything.
So here's what Carnot figured out. It's not about how much energy you have, it's about its quality. See, energy is most useful when it's all bunched up, when it's concentrated, like the hot, high-pressure steam inside an engine. But as that energy spreads out and cools down, it gets less and less useful for doing work. The total amount of energy is still there, sure, but it's now all dispersed. It's just not as useful anymore.
It took a few decades, but another physicist, a guy named Rudolf Clausius, finally gave this idea a name: entropy. And in the simplest terms, that's all entropy is. It's just a way to measure how spread out your energy is. Low entropy means the energy is concentrated and ready to do work. High entropy means it's all spread out and, well, pretty useless. And this quote from Clausius himself just perfectly nails the first two laws of thermodynamics. The first law, the energy of the universe is constant. You can't make it, you can't destroy it. And the second law, the entropy of the universe tends to a maximum. That energy is always, always, always spreading out.
But why? Right? What is this invisible force that's constantly pushing everything towards being more spread out? Well, the crazy thing is, it's not a force at all. It's just simple, straightforward probability.
To get your head around this, let's use a perfect analogy. Think about a Rubik's Cube. There is exactly one way, just one single configuration, where it's perfectly solved, right? Every color is perfectly lined up. That is its state of maximum order, its absolute lowest entropy state. Now, how many ways can that cube be scrambled? The number is it's insane. It's literally quintillions of different ways for it to be a total mess. And all of those scrambled states are high entropy states.
So if you take that solved cube, put it in a box, and shake it up, what are you going to get? A mess. Every time. Not because the universe loves messes or prefers chaos, it's just because there are overwhelmingly more ways for it to be messy than for it to be solved. The universe is just playing the odds, and it always moves from an unlikely state, like a solved cube, to a much, much more likely one. And that, right there, is why entropy always increases.
Okay, so that's the big idea. But how does this abstract concept about probability and spreading out actually connect to the world we live in? How does it connect to us?
Just think about an air conditioner for a second. It does something that really seems to defy entropy, doesn't it? It makes a room colder by taking heat from inside and concentrating it outside. It creates this little local pocket of order, of low entropy. But this doesn't break the second law, not at all. Because to create that one small pocket of order, the power plant that's fueling the AC is burning fuel and creating a way, way bigger amount of disorder, of high entropy somewhere else. You can fight entropy locally for a bit, but you always have to pay an entropy tax, and in the end, the universe always wins.
And this brings us to the most amazing example of all, life itself. I mean, life is the most incredible, complex, low-entropy thing we know of. So how does it pay that entropy bill? Well, let's just walk through it. First, the sun sends us a gift, concentrated low-entropy energy in the form of photons. Second, life, plants, animals, us, uses that energy to create order, to grow, to move, to think. But in doing so, step 3, it spits out a bunch of dispersed, high-entropy energy as heat. And finally, step 4, the Earth radiates all that high-entropy junk back out into space.
And just how big is this entropy tax that life pays? It's absolutely staggering. For every one high-quality, low-entropy photon that Earth gets from the sun, it radiates about 20 low-quality, high-entropy photons back out into space. We are fantastically good at increasing the total messiness of the universe.
So we're finally back at our original question, and now we have the answer. The sun's real gift isn't its energy, we send all of that back out into space. The real gift is its low entropy. It's a constant stream of order that lets us build the incredible complexity of life, all while paying our dues to the second law of thermodynamics.
All right, let's take this one final giant step up. We're going from life on Earth to the entire cosmos and to the very nature of time itself.
You know, the entire history of our universe is really just the story of entropy. It all began with the Big Bang, which was a state of incredibly low entropy. Then, as gravity started pulling things together to form stars and galaxies, entropy started to increase. Right now, we're in this amazing middle phase where all this incredible complexity can flourish. But this is all part of a one-way trip, heading towards an end state of maximum entropy, what they call the heat death of the universe, where everything is just cold, uniform, and nothing happens.
This constant, unstoppable journey from a less likely state to a more likely one. That is what we experience as the flow of time. It's why we remember the past but not the future, because the past had lower entropy. It's why you can't unscramble an egg. That would mean going from a super probable, messy state back to a wildly improbable, ordered one. This one-way street from order to disorder is the arrow of time.
And this leads to a really beautiful thought. The universe started out very simple, and its ultimate end will also be very simple and featureless. All the interesting stuff, all the complexity, the stars, the galaxies, the beauty, everything we call life, it's not the goal. It's just a temporary, magnificent thing that happens right here in the middle, during the universe's grand journey toward its most probable, most spread out state.
Which leaves us with one last, kind of wild thought to chew on. Life is spectacularly good at taking concentrated, low-entropy energy and turning it into spread-out, high-entropy heat. In fact, it's the best thing we know of at doing that. So is it possible that life isn't just some random accident, but is actually the universe's most creative and efficient way of spreading its energy out? Is it possible that all of this beautiful complexity is just the universe's most elegant way to make a mess?